the fact that if you look at the Gauss tension shift does not have to occur for this medium, does not have to occur for Brewster angle even. It can occur even for TE wave, K1Z minus K2Z over K1Z plus K2Z. Okay? For if the wave is evanescent in one region and propagating in another region, then this becomes something like this. Okay, there's no Brewster angle, no pole in this thing. But then because of this thing, you can write this as a unit amplitude. And this is unit amplitude because numerator and denominator are the same and complex conjugate to each other. This is just a phase shift. The reflection coefficient at total internal reflection is just a phase shift. Okay? What is a phase shift? A phase shift in the frequency domain is a what in the time domain? A delay. So this reflection coefficient actually gives rise to a delay. So you can do optical experiments. If you shine light at an interface and if there's a total internal reflection, you find that the light beam does not get reflected immediately, but it gets delayed before it comes back. And this shift is called the Gauss tension shift. Okay, so the Gauss tension shift is coming from this effect. Okay, not due to this lateral wave. It's entirely a phenomenon of total internal reflection and a phase function that comes from that. Okay. What else should we know? I guess that's all we should know. And in your homework, you're asked to evaluate this spherical wave in region 2. Okay. And there's a little bit of trick there because if you look at the setup point in region 2, it will be given by K2 sine theta. Instead of K1 sine theta, we always have K1 sine theta somewhere, right? Or K1 sine theta over here. So this is K1 branch point, K2 branch point. In your homework, then, if I were to draw the two branch points, K1 and then K2, the setup point can occur here. This is given by this formula. Okay, so if you go through looking for the SDP that goes through the setup point, it might look something like this. It will look something like this. Okay, not that way. Okay, it will look something like this, and then like that, and then actually it will occur in, not on the top Riemann sheet anymore because it crossed the branch cut once here. It crossed the branch cut 2 times there. By the time it emerges there, it's not on the bottom. It's not on the top Riemann sheet, so you cannot detour the SIP to it. On this other side, this side you can connect with the SIP, but you have to do something. Okay, you do something by finding the SDP through the branch points and the branch cut, and then add that one in, and then only you can close this part. Okay, that is your homework. Yes. Yes.
In that scenario, if material 1 is lossless and you have a very lossy material 2, then your two branch cuts will be very separated.
Right.
Then how? What are the? Is it true that the steepest descent paths must pass through both of the branch cuts?
No, not necessarily.
So
it can occur in that scenario that I drew before.
Exactly.
That one of the branch cut is lossless, the other one is lossy. Then your SDP might look something like this. Just pass through one of the branch cuts. Okay.
So it does actually go through the Riemann sheet where the hole is, right?
It's here. It's at the bottom most Riemann sheet. Okay, and then let me see. Where would that be? That would be in the top Riemann sheet of this steel. And then the pole might be here. Okay, the pole might be here, but I don't believe that it is near the is near the steepest descent path. That's my belief. Okay, I did not do it, but it's just a belief. Okay, the belief is due to intuition. Okay, is due to the intuition of rubber sheet deformation. I know that this pole is not going to be there for this geometry.
Are we assured that this pole must be on the other shore of that other branch part?
Not necessarily, not necessarily. But if I were to continuously change things, introducing laws, okay, and suddenly getting one of the branch cuts to continuously change. So it's like deforming rubber sheets in my mind, right? Deform these rubber sheets. And the pole was actually on the wrong sheet in the very beginning. I don't expect it suddenly to be on the right sheet, okay, in that picture over there. But if you go through the detail, I don't think you will find it in the bottommost Riemann sheet and that you will be encountering. Okay, so it's never truly contributing to a pole. You can do it as a project. Look at how this pole changes as you start to change the laws of region 2, whether it actually comes into your contribution. Some people say it does, but my belief is that it does not. Okay, that the surface wave pole never really contributes. But there's one scenario where it does contribute though. There's one scenario where that pole becomes a surface plasmon pole. The same equation that you have here, if epsilon 2 is negative, for epsilon negative material, like in optics, that you can encounter now, then what happens is that epsilon is negative, epsilon 2 is negative, okay? So this is negative, and if epsilon 2 is so much more negative that the denominator remains negative, this remains a positive number. This pole can still be found close to the ray axis. Okay, in that case, if I were to draw this picture again, and if I were to draw the K1 branch cut, K1 is over here. Okay, this thing says that I could have if epsilon 2 is negative and epsilon 2 is also negative, the pole could be here. It's real, okay, it's real. It's on the real line. This is the surface plasmon pole. Okay? And then I ask myself, what happens to the K2 branch point? K2 is now, K2 is omega mu epsilon 2. Epsilon 2 is negative, so K2 comes over here. K2 is over here. Okay. Now if you do the analysis again, SDP goes through the certain point like this, and so there could be an occasion where when you detour from the SIP to the SDP, you pick up this pole contribution. It's a surface plasmon pole. And remember, this location here is K1 sine theta. This other location is K1 over sine theta, which means that if theta is small, I don't observe it, but when theta is large, I observe it. Because if theta is small, this crossing point will be over here. Okay? If theta is small, this path might look something like this. And if theta is large, and this path looks like that, which means that if you remember what theta is, for the case of the dipole source right on the surface, theta is just this angle. Okay, theta is just that angle. So when theta is small, I would observe it because when theta is small, sine theta is small. Is this right? Theta is large, theta is small. When theta is small, I don't observe it. When theta is small, this number becomes large. Okay, so theta is small. But if theta is large, I'm closer to the surface. Okay, I start to pick up this pole. This is a surface wave pole. As we said before, this surface wave pole gives rise to a guided mode that looks something like that. It can only be observed near the surface. Okay, this is the surface plasmon. So the same pole manifests itself as the Zanic surface wave pole, the Sommerfeld pole, and the surface plasmon pole. The same pole, the same mathematical pole, manifests itself differently. Okay? Any questions regarding this? It's clear, right? Okay. It's very clear. And these are called critical point analysis. You have to know what the critical points are, and then you can pick up all these different contributions. Okay? So very good. You understand all this now. It's very complicated, but you understand it. You can see your brain has grown bigger. Okay? And things will become simpler when you look back. And because when I ask students to read chapter 1 of my book, they say it was very, very difficult. Well, now if I ask you to read chapter 1, it's very, very simple, right? So you become, because the brain has expanded. So let's talk about dipole on the slat then. This is quite interesting because you have a slat. There could be guided mode in the slat. This is the dielectric slat. You can have guided mode on this slat. How does this guided mode manifest themselves? Let's talk about the TE case. To make things simpler, then TE case, you look at H1Z, and if you look at the reflected wave, it will be a constant times this thing. And then times this reflection coefficient, which should be the generalized reflection coefficient of the TE type, okay, times the proper phase function, e to the ik1z z plus 2d1. And it's the thing that has changed. That is the only thing that has changed in this integrand. And that's where the physics has changed also. R12 tilde is now not the simple R12 of the Fresnel reflection coefficient, but something of this form, R12 plus R23 e to the 2I A2z. The thickness of the slat, okay, 1 minus R21 R23 e to the ik2zh. This is the generalized reflection coefficient. The reason why I can remember this is because of physics, not because of my good memory. I understand what each term meant, so I can write them down quite easily. But then there could be poles, right? There could be poles in the reflection coefficient now. Where are the poles located, and what equation should I solve in order to find the location of the poles now? Well, I solved the pole location by solving this equation. 1 minus R21 TE R23 TE e to the 2I K2ZH equal to 0. Right? Equal to 0. And those are the pole locations, and those are the locations where the reflection coefficient will become infinite. And as I asked you before, what is the physical meaning when the reflection coefficient is infinite? Not necessarily. What does it mean when reflection coefficient is infinite? Yes?
Like a resonance.
You hit the resonance, you hit the guidance condition. It means that there is a reflected wave, even when there's no incident wave. That's what it means. Okay, reflection coefficient is infinite means no incident wave, but there's a reflected wave. Right? Incident wave is 0, reflected wave is non-zero. Then if you evaluate the reflection coefficient is infinite. And that is the condition where you can have a guided wave in the slat without any incident wave. So this is the condition for guided waves, existence of guided waves. Now in the case of a cavity, this would be a resonance solution. Okay, in the case of a slat, it's a guidance condition. And I can actually use back the same diagram, I believe, to draw this thing, okay, to draw this thing. And say this is K1, this is K2, this is K3. It turns out that this will be functions of Kiz, right? K1z equals to the square root of K1 square minus K rho square. K2z equals to K2 square minus K rho square. K3z is equal to K3 square minus K rho square. How many branch points would there be in this problem? Yes? How many branch points should there be?
3 branch cuts. 3 branch cuts.
Okay. Okay. You got tricked. The correct answer is that there are only 2 branch points on the first quadrant, and then 2 branch cuts. Okay. There's no K2z branch point, and then no K2z branch cut. So this is a trick question. You didn't know the answer, that's why you got tricked. But I know the answer. Okay. There's no K2z branch point. Why is that so? I can argue that there's no K2z branch point in branch cut from uniqueness principle. Okay, from uniqueness principle. Say, if student one wants to solve this problem, a 3-layer medium problem. Student 1 would write down the solution K1z plus R e to the K1z z plus the phase function maybe 2D1 in region 1, right? Student 1 will write down the solution in region 1. Student 1 will also write down the solution in region 3 as something like this, minus sign with some transmission coefficient, 313, some unknown amplitude. And then he will write down the solution in region 2, AK2ZC plus B e to the minus A2ZC, right? Student 1 solves this problem. And then there's only one unique solution to this problem by using constraint condition, by matching boundary condition, okay? And he solved this problem, he got this R tilde. R tilde is very complicated. Seems to be a function of K1z, K2z, K3z, okay? If student B comes about and solve this problem just to be different, he put a plus sign and a minus sign there. He solved this problem again. Would he get a different reflection coefficient? No. Why? What is the reason that he wouldn't?
Standing wave, right?
The standing wave, right? And the solution in region 2 is still upgoing and downgoing wave. He wrote down the solution in region 2 in this fashion. Student 1 wrote down the solution in this fashion. It's still upgoing and downgoing, but it's still complete. He had given the complete solution in region 2. Student 2 also did the same. So student 2 just say e to the minus I K2ZZ plus b e to the I K2ZZ. And so he's going to get the same reflection coefficient R tilde. So what does this exercise point to you? It points to you to the fact that this R tilde is not going to be dependent on the sign of K2Z. It doesn't matter what sign I pick for K2Z. I get the same answer. Which means that R12 tilde TE must be an even function of K2Z. It must be dependent on K2Z squared. If it's only a function of K2Z squared, okay, couldn't be a branch point there. Okay? So this is the argument by uniqueness principle. If you don't believe me, go to the algebra and convince yourself. It's a lot harder to go to the algebra. And then you can do the same for the algebra of 3-layer, 4-layer, 5-layer medium. You can go to the algebra and K1z, Knz. And then you can write down the solution in each region as a linear full superposition of 2 waves. Okay? And then it wouldn't be dependent on the sign of KIZ, where I is 2, 3, 4, 5, and n minus 1. There's no branch points at all for this region, except for the first and the last region. Okay? Are you convinced of that? Or if you don't believe me, go and do the algebra. You spend a lot of time convincing yourself, okay, that actually the branch point does not exist for the intermediate region. So because of that, we only need to draw the branch point for the first and the last region. So let me call this K2 and this K3 then. Okay, I think this one, what I have in my. Maybe in my thing, this is K1. This is K3. Okay, and no pole, with no more Sommerfeld pole. So I use back the same picture. So there's no K2 branch point. K2 is somewhere else. K2 could be over here. Let's say K2 is over here. But it's not a branch point. It's just a location of the wave number K2. Okay? So where would the guided modes be in this complex plane? Guided mode must be having evanescent wave in region 3 and region 1. Okay? If the pole is over here, it will be evanescent in region 1, wouldn't it? Because K rho is larger than K1. If the pole is over here, okay, it will be evanescent in both region 3 and region 1. Okay? Can the pole having a K rho larger than K2? K2 is the slab region. Cannot, right? Because this is a bouncing wave. This is a bouncing wave. If the wave bounces around, okay, this K rho is essentially given by the component of this K vector. Okay. This K rho is never going to be larger than K2. So the poles are all going to be over here. But never larger than K2. Because it has to be a bouncing wave in region 2, the guided mode. So these are all the locations of the poles, just by physical argument. If you're not convinced of that, go and solve them. You find that all the guided modes are there. Evanescent in region 3, evanescent in region 1. Never having a wave number larger than K2, because it's a bouncing wave. Okay? And we'll see how these poles contribute. How these poles contribute later on. Okay, I think that's a picture I have. Actually, this is one possibility. The one in my textbook is slightly different. The picture is slightly different because I think in my textbook the K3 is less than K1. Okay, K3 is less than K1, so the picture is slightly more complicated. Okay, let's take a 5-minute break and we come back to trying to elucidate the physics of these poles. This pole actually becomes a leaky wave pole. Okay, leaky wave pole is an important concept because people do design leaky wave antennas. Leaky wave antennas uses the same physics as leaky wave pole, and we see how this pole become leaky wave poles. Okay, let's take a break.